Hi everyone, today is fun maths. 2 plus 2 equals to 5. Oh, what's this again? Today we are talking about inertia. What is inertia?
Hi everyone, today we'll be talking about Earth's magnetic field and specifically angle of inclination and declination. We all know that Earth is a giant magnet which acts as a bar magnet like the one we are seeing like this. It is actually inside the Earth's surface, not outside the Earth's surface. It is inside the Earth's surface in the outer core of the Earth's layer. So it has South Pole and North Pole, and the South Pole is near the geographic North Pole. Now, what is this geographic North Pole? We know that it performs two motion. It performs circulatory motion and rotational motion because it rotates about its axis and it circulates, which means it revolves around the sun. Now, this rotational motion, it performs it around its axis. So this axis of rotation, it is where we known as our North Pole and our South Pole. Our magnetic South Pole is the one that is at up here. So our North Pole, magnetic North, is down here, and it's because we know that unlike pole attracts while like pole repels. So unlike pole, South and North, they attract each other. So that's why South is up and North is down. The angle between the North Pole and the South Pole, the geographic North Pole and the magnetic South Pole, is what we mean by angle of inclination. It varies, it increases with time, but it's not a rapid increasing. When we suspend a magnet on the Earth's surface, it aligns itself, like the North Pole will come to the Earth's South Pole and the South Pole will turn like this. When we suspend a magnet, that's how it will turn. So it will turn to the Earth's magnetic South Pole and it will turn its South Pole to Earth's magnetic North Pole, and that is the basic of compass. Since the needle in the compass is magnet, then the South Pole of that magnet will turn to the North Pole of this magnetic pole, and the North Pole of that magnet, of that needle, will turn to the South Pole of the magnetic pole, making it look as if we are facing the geographic North Pole. Although if you are holding the compass, it helps us in navigating the road. If you are facing it and the needle is pointing north, it's not actually pointing to the geographic North Pole, it's pointing to the magnetic South Pole. That is what it is pointing at. So the deviation between this angle is what we mean by angle of declination. There are some ones that they will draw like this. They will draw the angle of rotation like this, like North Pole, like geographic North Pole and geographic South Pole, and they draw the magnets like this. Like this also. They can draw it like this also, such that the angle will not be too much like this one. So they can draw it also like this, but so it can be like this also, depending on where you are on the Earth's surface. Now let's now discuss the angle of inclination, which we also known as angle of dip. Now mind you, angle of declination is what we mean by angle of variation. Now for angle of inclination or angle of dip, it is the angle that this Earth magnetic field make with the horizontal, like with the Earth horizontal. We know that the horizontal on this Earth surface is not equal. Maybe here the horizontal will be here the horizontal will be here. At this place, horizontal is going to be different. So the angle here, it angles up, it goes up, and then later it comes down and enters the South Pole. So that is how it is. So we will zoom in now and we will see what angle of dip is. Okay, for a man standing on this Earth surface now, we know that the horizontal of this guy, the horizon of this guy is going to be straight like this. What we will be looking is like straight like this. That is the horizontal of the Earth surface that we mean by. So it's the horizontal at which a person can see at that Earth level. The magnetic field is angling up like this. You can see from here, we can see that it is angling up. You can see that the angle is going up. It's going up. So if you draw a straight line like this, you can just see that the angle is the magnetic field is going down like that. So we can now say that the angle formed by the horizontal and this magnetic field at that particular point is what we call angle of declination, and it varies on any earth surface. If the person is actually at this position, so if the person is standing like this, you will be seeing something vertical like this or something vertical like this. So the angle at which this thing is formed is what we mean by angle of dip, or the angle at which this thing is formed is what we mean by angle of dip. It can happen under also. And if you should look at the equator, we know the equator is like the halfway of this earth. If you look at the equator at this place, the person will be standing right like this. So if the person is standing like this, the horizontal of that person is still parallel to the magnetic field. That's why they say that at the equator the angle of dip is 0, and we can see that at the equator the horizontal is parallel to the magnetic field at that point. And at the pole, this is the pole. At the pole now, we can see that if a man is standing like this is the horizontal of that man, and the pole is actually coming downwards straight, so it is 90 degrees. So it angulates from 0 to 90 degrees, because at this equator it is 0 and it starts increasing till it reaches 90 degrees. That is for that, or I say from 90 degrees it starts reducing till 0, and it starts increasing again till it reaches 90 degrees. So if the person is standing right here, you can see that the horizontal of this guy is going to be like this, and if you should trace it, the angle formed will be something like this also. So the angle formed between the horizontal at that particular place and the earth's magnetic field, because wherever we stand on the earth surface, there is earth magnetic field that is going above us. So the angle at which the earth's magnetic field is going and the horizontal at which we are is what we mean by angle of dip. I hope you understand this video. And this earth magnetic field actually protects us from sun flare like this. So the sun wind, as it is blowing, the earth magnetic field is actually the one that is protecting us from it, because the sun wind, as it is, it is a charged particle. That solar wind can actually damage the human cell. So it's the earth magnetic field is protecting us from it. As this is coming towards the earth magnetic field is shielding us from it to get that direct contact from us, so it bounces off the earth's magnetic field. And this sun wind actually get trapped to the North Pole and the South Pole, and this North Pole and South Pole that get attracted to is the one that now cause aurora in this north and south region of Earth, like Canada being in North Pole, North South, and other countries, and Australia being in South Pole and other countries. They are the one that experience aurora, and aurora look like this. So this is the beauty nature of solar wind. But if the solar wind is directly towards the Earth, it's going to damage human cells, but the Earth magnetic field protect us away from it, and the North Pole and the South Pole get attracted, and this is what they see in Canada, Australia, like almost every night. But it has sometimes that the wind is always high, very high. So those times that the wind is very high, they will see it clean and clear like this, and sometimes they can just see it a little bit. That's the end of this video. Please like and share and comment. Thank you.